So in our last video, we had talked about the frequency multiplexing. That is where we stopped it. So we shall continue further with the other discussion, which is on the next kind of frequency demodulation, which is called the phase lock loop. Now this is quite an interesting one, okay, because whenever the carrier frequency of the transmitter and the receiver, they don't, basically synchronize with each other, the phase lock loop actually does the job of removing this kind of problem that exists. And it is also, one of the best frequency demodulation circuit that we have got. So PLL is basically a negative feedback system that consists of three different components. One is a multiplier, other one is a loop filter, which is also a low pass filter, and the third one is a voltage controlled oscillator. If you can remember, voltage controlled oscillator is also one of the kind of frequency modulation technique, which is called a direct method. A simple Hartley oscillator with a variable capacitor will make that particular circuit as a frequency modulator circuit. So the same thing is used even here also, a voltage controlled oscillator. Now who is controlling the oscillations of the VCO? It is V of t. And where is V of t coming from? The output of low pass filter. So initially, if you ask what is the output of the low voltage controlled oscillator, I would rather say it is nothing but now as I said, VCO is also equivalent to a FM. So what we can understand is, let me put that here. Okay, let me come back to this. Now this VCO output, if I call it as R of t, it is nothing but some amplitude value, let's call it as A. It will be cos of, within the bracket what you write will be the equation of FM, because VCO is nothing but a frequency modulator. And the angle part of this, or the phase part of this, is written as integral 0 till t V of t dt. Why? Because it is this V of t which is going to change the frequency of this VCO. Okay. Now where is this V of t coming from? Let's try to analyze it. So we'll start from the beginning here. So E of t is what you are applying here, which is the modulated wave, which is FM modulated wave. The other input is R of t, and the equation I've already written that here. So when those two basically gets multiplied, when E of t gets multiplied with R of t, let's call it as some E dash of t, because I've got E of t already written there. So E dash of t and R of t gets multiplied, and you get it as E of t, which is E dash of t getting multiplied with R of t. Okay. Now that becomes the input. Now when you try to simplify this equation, what you get is a low frequency component which contains the M of t part. And what is this E dash of t containing within it? E dash of t contains within it EC cos of, within the bracket, a term which has 2 pi fct. It also contains EM of t within it. Okay, this is integral 0 till t EM of t with a beta factor here. Okay, so this is what you basically get. Now only this beta times of EM of t will come into picture. Beta times of EM of t comes into picture here. So what are we trying to understand now? The output of the low pass filter would be containing only EM of t part. Now that's an interesting thing, because the entire operation is making me to get the required signal at the output of the low pass filter. And why is this feedback thing required here? So any change in the phase that happens will be nullified by this, and only EM of t part will be retained. So that's the reason why this kind of setup is used in the frequency demodulation or FM demodulation. Okay. So going on to the next one. So based on the equation what you get, you can write what is called the nonlinear PLL block diagram. So this entire equation is out of the equation what we just wrote in the previous slide. So you'll have two phase. One is phi1 of t, which contains integral 0 till t EM of t dt. Okay. So coming to the other part, that is this one. This contains within it phi2 of t, which will be integral 0 till t V of t dt. So these are the two phases that comes into picture here, and it generates phi e, which is nothing but phi1 of t minus phi2 of t, and a sine component basically gets appended to it. 2 pi k naught is also getting multiplied, and later on you pass it through the low pass filter, which is basically d by dt part, and you will get phi2 of t. And finally then you have a scaling factor, which is 1 over 2 pi k v, which is V of t, and that V of t is nothing but your EM of t. So this is how the demodulation process happens. Now in this particular block diagram, that is in this previous block diagram, which becomes the nonlinear part? It is this sign which is making this thing to become a nonlinear. Okay, now if you say sine theta, let us say, and if theta is very, very small, what will happen? The sine theta reduces to only theta, isn't it? Correct? Now, this concept is what is basically used. Okay, this concept is what is basically used in the entire process. Now, if you try to see this, let me write it here. Now, you can see theta part gets eliminated because I wrote it as only theta. Theta in this case is nothing but phi e. Phi e of t is nothing but equal to theta of t. Okay, just bear this in your mind. So this is what is happening there. Now the rest of the things is all same. If you try to observe this block with this, you do not see any other change except for the sign. Here it is there it is, not available. Okay, so this is how the demodulation process happens. Just hold on for a second. Okay. So moving on to the next one, which is about the super heterodyne receiver.